So if we think about 2 points in 3D, in 3 space, in R3, and what I want to do is derive this formula, the formula for the distance between 2 points. So P1 is the point x1, y1, z1, and P2 is the point x2, y2, z2. So they each have, they're three-dimensional, their x value, their y value, their z value. And here's our formula for the distance between 2 points. It looks very familiar because if I were to erase this part of it, then that would be the distance between 2 points in 2 dimensions, which we've seen before, but it's really just Pythagorean theorem, right? If I square both sides, the distance squared is equal to the distance between the x's and the y's. But let's do this in 3D. Thinking about that we already know the distance between 2 points in 2D. So here's a box. And if I want to think about then the distance between 2 points, let's make one point this corner, and let's make the other point the opposite corner. So I'm trying to find the distance between these 2 points. And if I call the x distance along this long part, the y distance along this part, and the z distance up, then I'm looking for these 2 distances here. Let's just think about the distance between not these 2 points, but these 2 points. So now there is no change in the z. There is no change in the z. The x runs along here and the y runs along here. So then if I'm thinking about what's the distance between these 2 points, there's a right angle, then I'm looking for this distance. Well, right angle, I can use Pythagorean theorem. What's this distance here? Well, that's supposed to be in the y's. So it's the difference between the y component of, the y component of 1 point and because the y component's the same for these 2 points. Remember, up and down here is in the z. So the y component here and the y component here. So I'm looking for this distance. That's just, it's either y1 minus y2 or y2 minus y1. Since I square it, it doesn't make any difference. So this distance here is just the magnitude of the difference between those y values. This distance along here, right over here, the magnitude of the difference between the x's. So this distance, from Pythagorean theorem, this distance is the square root of this squared plus this squared. So I've got the x1 minus x2 squared plus y1 minus y2 squared. That's this distance. Pythagorean theorem 2D, we knew that. But now, remember, I want to get the distance between this point and this point. So I already have this distance. Now, if I think about, I need another right angle triangle. A right angle triangle has a hypotenuse. That's what I'm trying to find, the distance between these 2 points. And it has 2 legs. The first leg is going to be this distance that I already know. The second leg is going to be this distance here. So this is one leg and this is another leg. And when I get those 2 legs, then the actual right angle triangle kind of cuts through this box, but it is a right angle on this corner. 1 leg, 2 leg. Now how do I find the distance then from here to here? The hypotenuse, it's going to be this magnitude squared. Well, if I square it, that just gets rid of the square root sign, plus this magnitude squared. This is in the z's, right? This is just z1 minus z2 absolute value. So if I square it, it's this squared plus this squared, and then square root the whole thing. Anyway, I've written all over my Kleenex box, but in the end, what have I made? I've made this distance between 2 points formula. And you know what? If you pause the video and go and get a box and a Sharpie, you can say your professor says it's okay to draw all over it and figure out this formula. And we can see that we've just extended our regular two-dimensional formula up by adding on, here was the x's, then the y's, then the z's. We've just added on another component. A lot of multivariable calculus is just that. We do what we would normally do in 2D, but we just add on a z dimension. We add on another dimension. In fact, if these points were four-dimensional, so if they had an x component, a y component, a z component, and let's say a w component, then we could make that four-dimensional formula by just adding on an extra piece for that last component. That would be the distance between 2 points formula in 4D. I couldn't draw it obviously on a box, but we see how the formula extend up one dimension from two-dimensional to three-dimensional. We did with the Kleenex box. Four-dimensional, we kind of just argued out that we should just add on the next dimension. Five, we could put I got to pick another letter. But what about going down then? Well, if I were to, I'm going to cut that out. That's our regular distance between 2 points formula in 2D that we're familiar with. If I were to remove, now this, squaring and then take the square root, that's another word for, or that's another way to write absolute value. So in one dimension, our points are just given by, there's only one dimension, so they're just given by their x coordinate. How far apart are two x values? You take the absolute value of the difference, and that's what this is. So the formula goes up and goes down by adding on the same, following the same pattern. So we can use this. So here's our first question using this formula. Do these 4 points form a square in 3D? Now, if they do form a square, then the distance between the points on the edges of the square, the distance between the points on the edges of the square have to be equal for it to be a square. And we all have to think about the right angle pieces as well. In other words, we grab some pairs of these points. There's 4 points, so there's 4 points to pick for the first point. There's 3 points to pick for the second point. So 4 times 3, 12 divided by 2, because first or second or first, doesn't matter. So there's 6 different ways that I can pick 2 pairs here. There's 6 points, there's 6 distances to calculate. If you calculate the 6 distances, 4 of them should be the same if this is a square, and the other 2 should be the square root of 2 times the shorter distances that are the 4. So do these points lie on a square just means what are the distance between all these 2 points? Are we getting 4 that's the same and 2 that are the same that are root 2 times the original 4? If so, square. If not, not a square. So it's a matter of using this formula 6 times. And I'll let you do this. Check. Let's do one example, and then I'll let you do the other ones. So let's find the distance. Let's find the distance between the first 2 points as like one of the 6 examples. So the distance between these 2 points. Now, 1, 1, 1, and 2, 3, 0. Of course, it doesn't matter which one I called point 1 and which one I called point 2. So working this out, this is going to be minus 1 squared or 1, minus 2 squared or 4. So let's just simplify this. Root 6. So the distance between those 2 points are root 6. If I grab another 2 points, let's grab these second 2 points here. I said I would let you do it, and here I am doing it, but let me just do this one more thing. So the x1 is 2, the y1 is 3, the z1 is 0, minus 1, so a minus is a plus 1, 2, and 0. When we evaluate this, root 10. All right, I think our question's answered actually, because they're not the same. Okay, so this root 6 might be the small and the root 10 might be the diagonal of the square, but root 6 times root 2 for a square isn't root 10, so yeah, it's not a square. So the answer to this is no, they're not a square. And notice, we could have even asked this as a four-dimensional problem, right? You could have a square in 4 dimensions. You'd have to still check this, but you'd have the plus w1 minus w2 squared in here. But we could go through the same argument. Lastly, let's take this distance formula, and I want to derive the equation of a sphere with the center, h, k, and l, and a radius, r. So what's the deal with a sphere, I guess I would say? Well, a sphere are all the points that are equidistant from the center. So all the points that are, let's say, x, y, z, and I'm going to make the center then is our h, k, l. So I'm just saying all the x, y, z points that are r away from. So this distance has to equal r. So I'm keeping the x1 is just x. The y1 is just y. The z1 is just z. And this is going to be the h and the k and the l. So now here's my formula, but I can square both sides. I think I will do that. If I square both sides, just to clean it up, to make it look like what we're normally used to, it's now equal to r squared. There's our formula, r squared. There's our formula for a sphere in 3D with center hk, l, radius r. Notice if I were to drop this piece, like drop it down to 2 dimensions, that's just the equation of a circle with center hk. So the shadow of a sphere would be a circle. The shadow of a 3-dimensional sphere would be like a 2-dimensional sphere, a circle. The shadow of a 2-dimensional sphere, a circle, would just be an interval. If I go backwards up, I can write, I can turn this into the equation for a hypersphere, a 4-dimensional sphere. So there'd be like W minus, this would need to be center HKLM, I guess. So now here's a hypersphere, a 4-dimensional sphere. I can't draw it, but I know what it is. I know this is the equation for it. And its shadow must be a sphere. The shadow of a 4-dimensional sphere is a 3-dimensional sphere. Let's go back. There's our equation of a sphere with radius r.